Today's date is December 1st, 1974. As the cold winter evening draws in, parked on stand at John F. Kennedy International, New York, is Northwest Flight 6231, a 5-year-old Boeing 727-200 series aircraft, listed on the US Register as November 274 Uniform Sierra. The circumstances surrounding this evening's flight will be somewhat unusual, in that neither the aircraft nor the crew should even be in New York. Earlier this afternoon, the 727 had operated a scheduled service from Minneapolis to Washington Dulles as Northwest Flight 336. In an ironic quirk of fate, the flight preceding them into Dulles was another 727, that being TWA 514, which incredibly crashed on its approach into Mount Weather, Virginia, with the loss of all 92 souls on board. Without delay in implementing their emergency response plan, the airport authority closed the airport to any further arrivals or departures, and as a result, Northwest 336 was instead rerouted to New York's John F. Kennedy. Following their arrival in New York, Northwest proceeded to make alternative onward plans for their passengers. But for the crew, however, at least for some of them, the afternoon wasn't yet over. News came through that the aircraft had been chartered by the Baltimore Colts football team to collect its players and entourage of management and support staff from the city of Buffalo in upstate New York, a short hop of approximately an hour and a half. As this entourage already comprised of the necessary complement of Northwest cabin crew, those cabin crew who had worked 336 into JFK were stood down and arrangements also made to facilitate their return to home base back at Minneapolis. That being the case, with the subsequent departure from JFK to Buffalo, the 727 will now only have a crew complement of 3. In command will be 35-year-old Captain John B. Legorio. Having been promoted to captain about 5 years before the accident, he will have accumulated a total of approximately 7,500 hours, with just under 2,000 of that having been obtained on the 727 itself. Occupying the first officer's seat will be Walter Zadra, age 32. He will have accumulated some 1,500 hours of total time in the right-hand seat, and an additional 3,000 hours as second officer or flight engineer on various aircraft type, about half of which will have been gained on the 727. His upgrade from second officer to first officer will have occurred only 5 weeks prior to the accident, with his conversion from the 707 type to the Boeing 727. And as such, he will have flown a very modest 46 hours in this new capacity. To the rear of the cockpit, operating the flight engineers panel for this evening's flight, will be 33-year-old Second Officer James Cox. His experience on the panel will extend to just under 2,000 hours, approximately 1,600 of which will have been acquired on the 727. The standard pre-flight weather dossier, which will be delivered to the crew, will include a synopsis of the current surface conditions and forecasts for both the departure and arrival fields, as well as relevant airports along the intended route of flight. In addition, the pack will include information regarding icing, wind and turbulence to be expected along the route. With the entirety of the flight expected to fall within the forecast window of 1,700 to 2,300 local, Legorio and his crew will have noted the anticipated conditions of moderate to heavy snow showers from Lake Michigan to the Appalachian Mountains, and moderate to heavy rain showers and scattered thunderstorms east of the Appalachians. A triangular area defined by lines connecting Pittsburgh, New York and Richmond, Virginia, indicated thunderstorms with tops above 28,000 feet. Furthermore, a significant meteorological observation, valid for the period between 1755 local and 2200 local, predicted frequent severe icing in cloud and precipitation above the freezing level, which was actually at the surface in southwestern New York and which sloped to 6,000 feet eastward towards the Atlantic coast. What will be recorded at JFK on the hour at 1900, some 15 minutes before departure, will be a light wind from the northeast under a broken to overcast ceiling at between 2,500 and 5,000 feet. Visibility in the area will be reported as reasonably good at 12 miles, with the surface temperature hovering just above freezing. The crew of a company aircraft on a similar route to the northwest, and which will depart JFK shortly after 6231, will subsequently report to the post-accident investigation team that they encountered icing and light turbulence in the climb. They stated that they were in instrument conditions from about 1,500 feet to 23,000 feet, except for a few minutes between cloud layers at an intermediate altitude. Northwest 6231 will depart JFK at about 19:14 local, and shortly after takeoff will disappear into the gloomy skies overhead. Airborne, Kennedy departure control will clear the flight to climb to 14,000 feet, with the aircraft subsequently being handed over to the New York area controller at approximately 19:20 and 21 seconds. Under his direction, the 727 will be further cleared to climb without restriction to flight level 310, the rough equivalent of 31,000 feet. As 6231 will turn and cross the coastline heading inland, the controller will continue to monitor its uneventful progress until, without warning, at 19:24 and 42 seconds, a mere 10 minutes after departure, the frequency will come to life with a sudden and alarming distress call from the aircraft, indicating that they will be out of control and descending through 20,000 feet. After giving interim altitude clearances at 19:25 and 21 seconds, the area controller will ask 6231 to state the nature of their problem, to which they will respond that they are descending through 12 and that they are in a stall. After this, most probably as the result of an involuntary crew action on the aircraft's push-to-talk switch, the sound of an active radio transmission will be heard, but there will be no further communication from the crew. Just 30 seconds later, at 19:25 and 57 seconds local, Northwest 6231, under the cover of darkness, will impact the ground within the confines of the Harriman State Park, approximately 3.2 nautical miles west of Thiels in upstate New York. Lagario and his crew will all perish. At first glance, the 727's departure had appeared procedural, routine, and completely unremarkable. So what had happened so rapidly during those 12 critical minutes after takeoff to cause the aircraft to quite literally fall out of the sky? This is the complete story behind Northwest Airlines Flight 6231. The aircraft struck the ground in a slightly nose-down and right-wing low attitude. The structure had disintegrated and ruptured and was distorted extensively, with no evidence of a pre-existing malfunction in any of the aircraft systems. The vast majority of the aircraft wreckage was found within an area 180 feet long by 100 feet wide. The horizontal stabilizer trim setting was set slightly nose up, with the landing gear and spoilers being retracted. The wing trailing edge flaps were extended to the 2-degree position, and the number 2, 3, 6 and 7 leading edge slats were fully extended, which is consistent with the trailing edge selection. The number 1 and number 3 engines were separated from their respective pylons, and the number 2 engine remained in its mounting in the empennage. The engines exhibited impact damage, but little rotational damage. The speed servo cams in all of the 3 fuel control units were at or near their high-speed detents. The outboard section of the left horizontal stabilizer had separated, with the inboard section remaining attached to the vertical stabilizer. The left elevator remained attached to the separated section. The right horizontal stabilizer was attached to the vertical stabilizer, except for the tip section, with the right elevator remaining attached to it. The 3 attitude indicators were damaged on impact. The indicators showed similar attitude information, that being about 20 degrees nose down with the wings almost level. The 2 pitot head heater switches were in the off position, and the switches toggle levers were bent aft. The damage to the switches and the debris deposited on them was consistent with what would have been expected if they had been in the off position at impact. Under investigation, a new switch with its toggle lever in the off position, when struck with a heavy object, exhibited internal damage similar to the damage found in the internal portions of the right pitot heat switch. 4 of the 5 pitot heat circuit breakers were operable and were electrically closed, indicating no specific technical fault with the circuitry. The auxiliary pitot head heater circuit breaker was jammed into its mounting structure and it was electrically open, this possibly as a result of the impact force. The left elevator pitot head was lying on the frozen ground. When retrieved, at least 8 drops of water dripped from its inlet. After exposure to sunlight, even more water was recovered from it. The captain's pitot head was retrieved and cleared of frozen mud, with its inlet port being filled with dry wood fibres. After exposure to sunlight, wet wood fibres were also removed from its interior, with moisture being present on the inner surfaces. The co-pilot's pitot head and the auxiliary pitot head were crushed and damaged severely, meaning that they could not be checked for water content. The right elevator pitot head remained attached to the vertical stabilizer, with its head being in good condition and containing no water or ice at all. The engine and the ice switches for the number 1 and number 2 engines were in the open position. The switch for the number 3 engine was in the closed position, and the switch handle was bent aft. Subsequent tests of the bulb filaments of the engine and the ice indicator lights showed that all 3 lights were on at impact. Thus, the condition of the number 3 switch being attributed to impact damage. In order to understand the significance of the investigators' findings in relation to the recovered probe heating panel, it's important that you get a good understanding of the pitot-static system, exactly how it works, and more importantly, how various failure scenarios impact on its operation. What the investigation team had found suspicious at the crash site was the fact that the probe heating panel from that portion of the cockpit located directly overhead the first officer's position was recovered with the heating switches in the off position, thus indicating that the relevant probes were not being heated at the time of impact, and one could assume had thus not been heated for a given portion of, or indeed all, of the preceding accident flight. This should not have been the case, as it introduces a vulnerability to possible environmental icing, which, this presentation will later show, can have a significant detrimental effect on the system's overall operation. Of note, and of significant relevance to the story of Northwest 6231, are the amber indication lights shown here which illuminate when a specific probe is unheated. These indicator lights were not fitted to the associated panel on the accident aircraft. Therefore, with the probe heat switches remaining in the off position, no visual confirmation of this fact would have been available to the crew other than the actual position of the switches themselves. And in a darkened cockpit environment, as was the case that evening, this would have been almost impossible to have picked up on. Such was the significance of this finding that the investigation team would ultimately include in their final report to the FAA a recommendation that such positive identification of system status be made mandatory on all aircraft types. On the 727, the pitot probes in particular are located on either side of the forward lower fuselage. Below the captain's sliding window is located a single pitot probe. Dynamic pitot pressure sensed here is fed to the captain's airspeed indicator and Mach meter. Further aft on the same side of the fuselage, the port-static sensor, in conjunction with a similar sensor on the starboard side of the fuselage, presents static information to respective captain and first officer pressure instruments, namely the airspeed indicators, Mach meters, altimeter, and vertical speed indicators. This fitting of a second interconnected static port probe on the starboard side of the fuselage allows for an average, more accurate reading to be used, particularly when localized pressure readings may potentially fluctuate, specifically when the aircraft yaws around its vertical axis. Finally, as was the case on the captain's side of the aircraft, on the forward fuselage just below the first officer's sliding cockpit window are located two pitot probes. One services the first officer's pressure instruments, as was the case with the captain, while the second probe, named the auxiliary pitot probe, furnishes information to the Mach airspeed warning switch, the autopilot, and the flight data recorder. In addition to the pitot-static systems which provide invaluable pressure data to the cockpit instrumentation, there's also two additional systems physically incorporated into the aircraft's artificial field system. In principle, the artificial field system is designed to provide an opposition or resistance to the pilot's movement of the flight controls, proportional to the aerodynamic loads being experienced on these controls. In other words, through these dedicated pitot-static systems, depending on the environment the aircraft finds itself in, the pilot's input on the flight controls will be regulated in order to ensure that hydraulic repositioning of the surface will never cause aerodynamic loading in excess of design specifications. With regard to the 727 type, the two respective pitot probes associated with these systems are positioned one on either side of the vertical stabilizer. In an effort to provide some background information as to how these various pressure sources interact with the various cockpit instruments, what's shown here is a rudimentary pitot-static simulator. Let's be clear, the depiction here is not a true representation of the 727 system. Rather, the presentation is more generic in nature. However, that said, the fundamentals being discussed differ little between aircraft type, from the single-engine Cessna 172 to the Airbus A380 or Boeing 747. The three pressure instruments depicted represent the airspeed indicator, the vertical speed indicator, and the altimeter. Additionally, the various pressure lines to these instruments are depicted as the static line, shown here in green, and the pitot line, shown in red. Furthermore, the actual pressure in each line is digitally displayed for comparison purposes, and becomes more relevant when we progress to discuss various potential failure scenarios. So let's start with the basics. As engine power is applied and the aircraft accelerates, the dynamic pressure sensed at the pitot probe inlet, represented here by the red line, will increase naturally enough, as environmental air has been effectively rammed into the pitot probe with the aircraft's forward movement. It's important to note, though, that the total pressure in the red pitot line is a combination of both this dynamic pressure and the ever-present static pressure which continuously surrounds the probe. As the aircraft in this example continues to maintain the same altitude, that being 8,000 feet, there will be no change to the environmental static pressure being sensed by the three pressure instruments, represented here by the green line. Therefore, as the aircraft accelerates, the combination of dynamic and static pressure sensed in the red line will be balanced against the static pressure alone sensed in the green line. In so doing, the static information in both the red line and the green line will cancel each other out, leaving a pressure differential between the two which is proportional to the dynamic pressure being sensed. It is this dynamic pressure which can be presented as a manifestation of airspeed on the airspeed indicator. As the aircraft decelerates, the reverse happens. Again, if the aircraft continues to maintain a constant altitude, then the static pressure sensed will once more remain constant across all three instruments. As the aircraft slows, the magnitude of dynamic pressure entering the pitot probe will correspondingly decrease, resulting in a decrease in the pressure differential between the pitot and the static lines, and hence an observed reduction in indicated airspeed. So dynamic pressure increase, airspeed is increasing. Dynamic pressure decrease, airspeed is decreasing. Now let's explore what happens to the pressure instruments when the aircraft climbs or descends. For the purpose of the demonstration, let's assume that the aircraft will maintain a constant indicated airspeed during the maneuver, shown here at about 140 knots. As the altitude increases, the drop-off in atmospheric pressure will result in an equally reducing static pressure being sensed across all three pressure instruments. With regard to the altimeter, this reduction in measured static can be directly correlated to the higher altitude, with the rate at which the static pressure sense is changing being indicative through the vertical speed indicator of how fast the aircraft is actually climbing. Under the circumstances, again with no appreciable change in the dynamic pressure being sensed by the pitot probe, and with the static pressures being sensed in the red pitot and the green static lines again cancelling each other out, the indicated airspeed will remain constant. In the context of a straightforward descent, all three pressure instruments will sense an equivalent increase in static pressure. As before, the altimeter will be calibrated to express this increased pressure sense as a decrease in altitude, logically given that atmospheric density increases as we move in a direction towards sea level. The vertical speed indicator will again sense how quickly this change is occurring, and in this instance will display such information as an indicated rate of descent. As was the case with the previous climb scenario, we have chosen here to assume that the aircraft continues to maintain a constant airspeed throughout the manoeuvre. Thus, with no change in dynamic pressure being sensed by the pitot probes, and static pressure balanced between the red and the green lines, once again, the indicated airspeed will remain constant at 140 knots. It's when we move on to discuss the potential environmental impact on the pressure instruments that things start to become a little more complicated. When I talk about the environmental impact here, what I'm really referring to is a situation where the pressure sensing ability of the pitot or the static ports is compromised due to a blockage caused by frozen water or ice crystals. Although such environmental blockages are significant hazard, physical obstructions are also possible, most notably due to insects nesting in the probes, or on occasion post-maintenance where aircraft have been dispatched with blanks or protective covers having been inadvertently left in place. Depending on whether the obstruction is in the pitot or static port, or indeed both at the same time, the impact on the associated pressure instrument can be very different. The presentation to the left of the screen is split into two halves. The upper half will depict the impacted pressure instruments, while the lower half, labelled as reference system, will show a comparative view of how the system would present without any blockage being present. So let's initially look at the impact a blocked static port would have on information presented to the crew. The most obvious impact will be on the altimeter and vertical speed indicator, as both exclusively sense static pressure. As the aircraft climbs, a blocked static port will mean that the reduction in atmospheric pressure associated with the higher altitude cannot be sensed, and thus the altimeter will fail to register any change in altitude from the value it was displaying at the time the blockage occurred. In other words, in the example shown, as the blockage occurs with the aircraft level at 8,000 feet, the altimeter will continue to erroneously display this value as the aircraft climbs. With no change in static pressure being sensed, the resultant effect on the vertical speed indicator is that, despite the aircraft physically climbing, this instrument will fail to register any such manoeuvre, and the value presented will erroneously remain at zero. The situation, however, with the pitot line is a little more complex, as it senses both dynamic and static pressure, with the origin of this static input being physically different from that of the static port. This significant fact means that despite the static ports themselves being blocked, at least in this example, the pitot probe will continue to sense static pressure as normal. Therefore, assuming again that the aircraft climbs at a constant speed, in other words with a constant dynamic pressure being maintained at the pitot port, an overall pressure reduction will be sensed in the red pitot line, as the sensed static pressure will start to drop off as the aircraft climbs. Thus, as the total pressure in the pitot red line starts to decrease with altitude, the resultant pressure differential between it and the trapped static pressure inside the green line will likewise start to reduce. What's important here is that as this pressure differential between the pitot red line and the static green line starts to reduce, the airspeed indicator interprets this as being a classic example of what normally happens when the aircraft decelerates. Hence, as the aircraft climbs with a blocked static source, the indicated airspeed begins to decrease. Note again that the lower half of the screen depicts how the system will behave without any blockages present. In the absence of a blockage, given the conditions in this particular example, the reference system will continue to display a constant speed during the climb manoeuvre. Having climbed 8,500 feet as indicated by the reference system, now let's see what happens when we descend and once again return to our original altitude of 8,000 feet. As seen with the climb scenario, the block static port ensures that both the altimeter and the vertical speed indicator continue to remain fixed at the aircraft's altitude coincident with the moment the blockage occurred. The only clue to the crew, therefore, that a problem exists is through the abnormal behaviour of the airspeed indicator. Again, basic physics dictate that as the aircraft descends, the static pressure of the environment surrounding it will increase. While maintaining a constant dynamic pressure into the pitot probe during the descent, the red pitot line will however sense an overall increase in pressure due to its additional unobstructed sensing of the static environment surrounding the aircraft. The differential between the total pressure sensed in the red pitot line and the trap static in the green line will thus increase, which the airspeed indicator will interpret as an acceleration, so that the act of descending the aircraft will result in an increase in indicated airspeed. To summarise therefore, with a blocked static port, any effort to climb the aircraft will result in the indicated airspeed appearing to decrease. Conversely, any attempt to descend the aircraft will cause the airspeed to increase in magnitude. All the time, the vertical speed indicator remaining fixed at 0, indicating neither a climb nor descent, with the altimeter remaining fixed at the altitude coincident the moment the blockage actually occurred. Now to specifically look at blockages which might impact the pitot probe sensitivity. The design of all pitot probes incorporates a drain hole, whose purpose is to allow precipitation which might naturally enter the probe through its inlet to, drain away, thus mitigating the possibility of this fluid freezing and causing those exact blockages which we're trying so hard to avoid. Specifically, with regard to a blockage of the drain hole, as the pitot-static line from the pitot probe isn't actually interfered with in any way, and as the static line to the vertical speed indicator and altimeter originate from a completely different source, a drain blockage will have absolutely no adverse impact whatsoever on system operation. Note the example firstly demonstrating the aircraft commencing a climb from 8,000 feet. In reverse, same scenario, but this time with a descent back down to 8,000. Again, no adverse impact on system operation. Exploring the effect on the pitot probe still further, this clip demonstrates the impact of a pitot inlet blockage. As the red pitot pressure line is a combination of dynamic and static pressure, once the inlet to the probe becomes blocked, the airspeed indicator sensitivity to dynamic pressure is immediately lost, resulting in only ambient static pressure being sensed by the instrument through the drain hole, which, as we said previously, is vented to the environment outside. Under such conditions, with loss of all dynamic pressure, the pressure in the red pitot line and that in the green static line will be exactly the same, both now simply sensing the ambient static pressure, with the pressure differential between the two falling to 0. With this differential between the two lines equating to 0 and dynamic pressure having been lost completely, the airspeed indicator will continue to display a 0 value regardless of how the aircraft is manoeuvred, be that in a climb or descent. By far the more complex failure is where water enters the probe and freezes in the drain hole, followed subsequently by a blocking of the pitot inlet. As the static sensing to the altimeter and vertical speed indicator remains unaffected, these two instruments continue to function as normal. With regard to the pitot probe, however, things are not so straightforward. With the ultimate blockage of both the drain and inlet, the pitot probe becomes effectively sealed, with the pressure within now being maintained at a constant, regardless of how the aircraft is subsequently manoeuvred. That being the case, as the aircraft climbs, the static port will sense a reduction in ambient atmospheric air pressure. Thus, the pressure reading in the green line will decrease. However, as the pressure in the red line is effectively fixed at a constant value, this pressure reduction in the green line will result in an increased differential between the red and the green, being erroneously interpreted by the airspeed instrument as an acceleration or increase in dynamic pressure. And as such, the indicated airspeed will appear to increase in magnitude. The reverse is true in descent. Again, as the aircraft descends, the sensed static in the green line will increase. As the pressure in the red Pitot line remains constant, the differential between the two will also reduce, a trend which the airspeed indicator will erroneously interpret as a deceleration or reduction in dynamic pressure, and as such, the indicated airspeed will appear to decrease. In summary, therefore, with the completely blocked Pitot probe, inlet and drain, any effort to climb the aircraft will result in an erroneous indication of increasing airspeed, while conversely in descent, the airspeed indicator will erroneously display a reduction in indicated airspeed. Finally, although extremely unlikely, with the combination of blocked Pitots and static ports, all three instruments are rendered completely useless and remain fixed at the displayed values coincident with the exact time the blockages occurred. It should be noted that the blockage scenarios I've depicted here are absolute, meaning that all blockages are total. In reality, however, the likelihood is that most blockages will be partial in nature, meaning the effects observed may be somewhat lesser in magnitude than those depicted, and possibly more transitory than permanent. Alert now to the possibility that the probe heating elements may not have been energized for the duration of the flight, and conscious of the implications of such a scenario, the investigation team turned their attention to the flight and cockpit voice recorders in an effort to search for possible corroborating evidence which might support their suspicions. The flight data recorder and cockpit voice recorder correlation showed that the aircraft's climb to the initial altitude of 14,000 feet was completely uneventful. Once level, it remained at this altitude for approximately 50 seconds, during which time the airspeed increased from 264 knots to 304. During that 50-second period, the airspeed trace showed two aberrations in a 27-second period. Each aberration was characterized by a sudden reduction in airspeed. The magnitude of these reductions were 40 knots and 140 knots, and lasted for 7 and 5 seconds respectively. The aircraft then began to climb at 2,500 feet per minute, while maintaining an airspeed of about 305 knots. As the altitude increased above 16,000 feet, the recorded airspeed began to increase. Subsequently, it was noted that the aircraft's rate of climb continued to increase, and as it did so, the indicated airspeed was observed to follow suit. So the faster the aircraft climbed, the faster it appeared to be going. About this time, the first officer commented,
"Do you realize we're going 340 knots, and I'm climbing at 5,000 feet a minute?"
The crew discussed the implications of the high airspeed and the high rate of climb, with the flight engineer commenting,
"That's because we're light."
After which the captain said,
"I wish I had my shoulder harness on. It's going to give up pretty soon."
With the rate of climb eventually exceeding 6,500 feet per minute. The sound of an overspeed warning horn was recorded as the altitude reached 23,000 feet, and at that time, the recorded airspeed was 405 knots.
Would you believe that shit? I believe it. I just can't do anything about it. Just let her back. Let her climb.
The last comment made by Legario here was followed by the sound of a second overspeed warning. It was now that events in the cockpit suddenly became a lot more confusing, as within 10 seconds of this overspeed warning being triggered, the CVR recorded the stall warning stick shaker being intermittently activated. The aircraft was now indicating to the crew that it was experiencing both an overspeed and underspeed condition at the very same time. 5 seconds later, the vertical acceleration reduced to 0.8 g as the aircraft crested the top of the metaphorical hill and started down the other side. It had reached an altitude of 24,800 feet and a recorded erroneous airspeed of 420 knots. The stall warning began again and continued while the first officer commented,
"That's the mock Buffett."
Legario replied,
"Guess we'll have to pull it up."
To 2 seconds later, about 13 seconds after the aircraft had arrived at 24,800 feet, the vertical acceleration trace again declined to 0.8 g, and the altitude trace began to descend at a rate of 15,000 feet per minute. The airspeed trace decreased simultaneously at a rate of 4 knots per second, and the magnetic heading trace changed from what was almost due west to due east within a 10-second period, which indicated that the aircraft was turning rapidly to the right. As the aircraft continued to descend, the vertical acceleration trace increased to 1.5 g. The aircraft's magnetic heading trace fluctuated, but moved basically to the right. About 10 seconds after the descent began, the Mayday call was transmitted. 33 seconds later, the crew reported,
We're descending through 12. We're in a stall.
About 5 seconds after that transmission, Lugario commanded,
Flap 2.
and a sound similar to movement of the flap handle was recorded by the CVR. There was no apparent change in the rate of descent. However, the vertical acceleration trace increased immediately, with peaks up to 3g. The recorded airspeed decreased to 0, and the sound of the stall warning became intermittent. 5 seconds after the captain's command for flap, the first officer said,
Pull now. Pull.
10 seconds later, the peak values for vertical acceleration increased to 5g. The rate of descent decreased slightly. However, the altitude continued to decrease to 1,090 feet, the elevation of the terrain at the accident site. The aircraft had descended from 24,800 feet to impact the ground beneath in just 83 seconds. In summary, what the flight data recorder had conclusively proven was that 6231's departure and initial climb to 14,000 feet was completely unremarkable. The first indication of anything which could have been considered abnormal or somewhat out of the ordinary were 2 sudden and pronounced transient drops in indicated airspeed. Whether the crew actually observed these events was never recorded, although the absence of any comment on their part being picked up by the cockpit voice recorder would suggest that they hadn't. Had they, then perhaps their suspicions in relation to the health and well-being of their aircraft would have been aroused. But again, the recorders suggest otherwise, and in receipt of a revised altitude clearance, Lugario, without hesitation, commenced further climb to their proposed cruising level of 31,000 feet. As the aircraft passed through 16,000 feet, investigators noticed a performance anomaly with the jet, which simply didn't seem right. As altitude increased, there was a similar, corresponding and correlated increase in indicated airspeed as well. And with the jet climbing with a constant power setting from all 3 engines, this simply shouldn't have been the case. As the aircraft commenced climb from 14,000 feet, a fixed value of climb power would have been set on all 3 engines. This fixed value of engine power would have resulted in a particular rate of climb for a given airspeed. Without adjusting this engine thrust, if the pilot were to subsequently increase the aircraft's rate of climb, then this new relationship between engine power, rate of climb and airspeed would be out of balance and would no longer facilitate a continued climb at the same airspeed as before, with the indicated airspeed value being seen to decrease. Alternatively, were the rate of climb to be decreased, then with a fixed engine power, the observed indicated airspeed would be seen to correspondingly increase in value. These being simple statements of scientific fact, what the investigators had uncovered was evidence that the cockpit instruments on board 6231 had displayed something very different. As the situation developed, the unusual and unexpected relationship between the aircraft's rate of climb and airspeed was commented on by the crew. Yet there was no evidence that they had conclusively attempted to rationalize exactly why. On the contrary, they had chosen to reconcile what they were experiencing with the fact that the aircraft's weight was extremely light. The investigation team, however, armed with evidence recovered from the crash scene, began to suspect otherwise. Having retrieved wreckage which conclusively proved that the pitot probe heater switches had not been turned on at the time of impact, and assuming that this had been the case for the entire duration of the flight. This trend of increasing airspeed with increased altitude to them portrayed all the classic characteristics of a blocked Pitot probe scenario. The further they dug, given the crash scene evidence, the environmental conditions on the day, and now the data from both the cockpit and voice recorders, the more plausible this hypothesis was becoming. Yet still there was no smoking gun, and furthermore, why had blocked Pitot probes, if indeed that was the case, result in the aircraft simply falling out of the sky? In an effort to resolve these questions and put their hypothesis to the test, the investigation team headed back to the laboratory. A metallurgical examination of the separated heater-conductor wire in the Pitot head from the first officer's Pitot system revealed none of the characteristics one would expect had its failure occurred while at an elevated operating temperature, suggesting that it was not carrying any electrical current at the moment of impact, thus validating the physical evidence they had already recovered. In an effort to examine what the implication of such a finding might be, a Pitot head of this same type was exposed to icing conditions in a wind tunnel, with the Pitot heater deliberately rendered inoperative. 1 to 2 inches of ice formed over the pressure inlet port. During this exposure, a thin film of water entered into the probe itself, some of which flowed out of the drain hole. Blockage of the drain hole by ice seemed to depend on the length of time required for ice to form and block the probe's inlet port. It was noted that the longer it took for ice to form and block the inlet port, the more likely it became that the drain hole would also be blocked by ice. Likewise, tests proved that the greater the angle between the longitudinal axis of the Pitot head and the relative wind, the greater the likelihood that the drain hole itself would subsequently become blocked. In an effort to reproduce the apparent inconsistencies between the airspeed and the altitude values of the flight data recorder, tests were conducted with an airspeed indicator and an altimeter connected to vacuum and pressure sources. By altering the vacuum to the altimeter and to the airspeed indicator, the various traces could be reproduced. However, following ascent above 16,000 feet, the flight data recorder airspeed and altitude values could be simultaneously duplicated only when the total pressure to the airspeed indicator was fixed at an altimeter reading of about 15,675 feet and an indicated airspeed of about 302 knots. This would suggest that the first aberration observed at 13,500 feet were indication that the Pitot probes were starting to become blocked. But as subsequent trials demonstrated and accident traces for altimeter versus airspeed suggested, the complete blockage of inlet and drain most probably only happened as the aircraft climbed to 15,600 feet. In a continued effort to validate their blocked Pitot hypothesis, the investigation team sought the assistance of the aircraft manufacturer in attempting to conclusively establish whether the airspeed and rate of climb combination as observed by the crew was even physically possible. If the manufacturer's evidence suggested not, then this would undoubtedly reinforce their suspicions. Thus, the safety board requested that Boeing analyse the data from the cockpit voice recorder and the flight data recorder to determine firstly the consistency of this data, particularly the airspeed and altitude values, with the theoretical performance of the Boeing 727. Secondly, the significance and possible reason for a simultaneous activation of the overspeed and stall warning systems. And thirdly, the body attitude of the aircraft during its final ascent and descent. Boeing subsequently verified the fact that the airspeed and altitude values which were recorded were consistent with the aircraft's predicted climb performance until the aircraft reached 16,000 feet. The simultaneous increase in both airspeed and rate of ascent, which were recorded thereafter, did exceed the theoretical performance capability of a Boeing 727-200 series aircraft of the same weight as the accident aircraft. In other words, the speed and rate of climb combination being displayed on the cockpit instrumentation simply wasn't physically possible. Consequently, the recorded airspeed values were suspected to be erroneous, and it appeared that they varied directly with the change in recorded altitude. That being that the magnitude of the error appeared to increase as the aircraft's altitude increased, with the recorded airspeed correlating to within 5% of the theoretical airspeeds which could be expected if the pressure measured in the Pitot system had remained constant after the aircraft's climb through this particular altitude. The indicated airspeed of the aircraft when the stick shaker was first activated was calculated to be 165 knots, as compared to the 410 knots recorded by the flight data recorder. The true decrease in airspeed from 305 knots to 165 knots as the aircraft climbed from 16,000 to 24,000 feet within a time frame of just 116 seconds was indeed theoretically possible, resulting in the aircraft's pitch attitude being about 30 degrees nose up at stick shaker speed was approached. The stall warning stick shaker is activated by angle of attack instrumentation, which is completely independent of and therefore not affected by errors in the aircraft's airspeed measuring system. It's for this reason that conflicting information from two separate independent sources could indeed, and in this case obviously did, activate both the erroneous overspeed and valid stall warnings at the very same time. Vertical acceleration reduced slightly as the aircraft levelled at 24,800 feet, probably because the pilot relaxed back pressure being applied to the control column. The stick shaker ceased momentarily, with this action resulting in an associated reduction in G-loading on the airframe. However, the aircraft continued to decelerate because of the drag induced by the still extremely high body attitude, and the stick shaker reactivated. Boeing personnel interpreted the sound of the landing gear warning horn on the cockpit voice recorder to indicate that the thrust levers had been retarded to idle. This most probably an instinctive crew response to the ever-increasing indicated airspeed. The second reduction in vertical acceleration to 0.8 g, which was coincident with a sudden descent and a rapid magnetic heading change, was probably caused by an aerodynamic stall with the probable loss of lateral control. In context, what we mean here by an aerodynamic stall is that as the aircraft climbed with the pilots inputting continuous nose-up commands in an effort to mitigate the ever-increasing indicated airspeed, the relative angle between the wing and the airflow over it continued to change. Specifically, this relationship, known as the angle of attack, continued to increase in magnitude. One of the recognised principles of aerodynamics is that as the angle of attack increases, so too will the lift being generated by the wing, up to a given point. As the angle of attack increases beyond this critical value, the airflow over the wing's upper surface is no longer capable of adhering itself to the wing surface, and consequentially detaches. The previously smooth airflow now becomes turbulent, lift is lost, and the wing is said to have stalled. Specifically with regard to Northwest 6231, this occurred quite rapidly as the aircraft climbed above 16,000 feet. Up until this point, the relationship between thrust, body attitude and angle of attack remained fairly balanced. From the diagram on the left, it can be seen that the airflow over the wing had good adherence to the upper surface. In light of the data recovered from the flight recorders, the investigation team were fairly convinced that the unheated Pitot probes began to block due to environmental icing, soon after the aircraft passed through 16,000 feet. What we also know is that such a blockage of Pitot probes, assuming that both the inlet and the drain holes are simultaneously blocked, will result in an erroneous increase in indicated airspeed with increasing altitude. That being the case, the crew of Northwest 6231, observing this increase in airspeed and failing to understand its significance, raised the nose of the aircraft in an effort to mitigate this increasing trend. What they were essentially trying to do was trade airspeed for altitude, or more scientifically, convert kinetic energy into potential energy. However, in pulling the nose up and increasing the aircraft's altitude, unbeknownst to them, all they were actually doing was making our bad situation worse. Perceiving that their efforts had been ineffective, the crew pulled still further on the control column, further increasing the rate of climb, which further increased the aircraft's altitude, which in turn still further increased the erroneous value of airspeed. And so the cycle continued. In the background, however, what was actually happening was that with a fixed power setting on all three engines, this increasing rate of climb was rapidly depleting the aircraft's energy state and simultaneously increasing the wing's angle of attack to the relative environmental airflow. As the angle of attack increases, the wing actually produces more rather than less lift, meaning that at this juncture the rate of climb being demanded by the crew was easily achievable. But with a finite amount of power being available from the aircraft's engines, and its energy being consistently depleted in an effort to satisfy the crew's consistent demand for even greater climb rates, sooner rather than later, something was going to have to give, as the relationship between thrust, body attitude, and angle of attack started to unravel. With the increase in angle of attack comes a corresponding loss of the aircraft's actual airspeed, and under conditions of 1G, meaning no additional loading on the airframe, the critical angle of attack and hence the stall will thus be reached at a specific speed, decelerating at a rate of approximately 1 knot per second. Once the buffer to this stall speed had reduced to about 7%, the stick shaker will have been triggered, alerting the crew to the impending danger. Here, each of the 2 control columns in front of the pilots will physically vibrate, producing both the tactile and oral warning to the pilots that the angle of attack has reached a dangerous level. What is almost counterintuitive here, however, is the fact that at this juncture, with activation of the stall warning, the wing is actually producing almost maximum lift. On activation of the stall warning, the message to the crew is that although the wing is not actually stalled yet, the aircraft has entered a phase known as the approach to stall. Correspondingly, in most aircraft types, as the critical angle of attack is approached, a level of aerodynamic buffeting can be felt as the airflow over the wing begins to separate. The 7% buffer is mandated by regulation so that the crew be alerted in sufficient time so as to allow for corrective action to be taken. In this context, the crew must first and foremost push forward on the control column in order to reduce the wing's angle of attack, thereby restoring again a healthy margin to the stall. However, specific to these T-tail configurations, as we've already mentioned, to mitigate against the crew's inaction or inappropriate action, some regulators, of which the FAA unfortunately was not one, also mandated a stick pusher, where a pneumatic ram would physically apply forward pressure to the control column, under circumstances where the angle of attack continues to increase. Where the pusher is not present, failure of the crew to identify and correct the situation will inevitably result in the wing reaching its critical angle of attack, known as CL max. At this point, the airflow above the wing separates and lift, although not completely lost, dramatically reduces, to the point where the wing can no longer support the weight of the aircraft. As pitch attitude increases, an aircraft with a low-set tailplane, such as the 737 for example, will suffer from its tail being immersed in the wing's wake, which is slightly turbulent, low-energy air. This generates the accompanying aerodynamic buffeting, which serves as a warning sign of impending stall. In such circumstances, the reduced effectiveness of the tail acts to resist any pilot effort to effectively force the aircraft any further into the stall. With these low tail configurations, once the wing does stall, as indicated here in the diagram, the wing's wake passes more or less straight rearward and above the tail structure. The tail is now immersed in high-energy air, where it experiences a sharp increase in positive angle of attack, causing upward lift, ultimately assisting with the nose-down pitch and decreasing the wing's angle of attack, essential for any stall recovery. In the case of a swept-wing jet with a T-tail and rear fuselage-mounted engines such as the Boeing 727, the situation develops somewhat differently. The handling qualities down to the stall are much the same as with the low-mounted tailplane, with a significant exception being the fact that the high T-tail remains clear of the wing's wake initially, thus providing little or no warning in the form of pre-stall buffet. Also, the tail is fully effective during the speed reduction towards the stall and remains effective even after the wing has begun to stall. This facilitates the undesirable effect of the pilot being able to drive the wing into a deeper stall at a much greater angle of attack. At the stall, as with all swept-winged aircraft, the tendency for the nose is to pitch up rather than down. This characteristic tendency is caused by the swept wing's design giving rise to the development of a strong span-wise airflow towards the wingtips at these high angles of attack. This leads to a tendency for separation of airflow and the subsequent stall to occur at the wingtips first. That being the case, as the wingtip stalls in advance of the inboard section, the centre of lift will shift in a forward direction relative to the centre of gravity of the aircraft, causing the nose to pitch up. Hand in hand with these increased angles of attack is a punishing increase in drag, resulting in the aircraft beginning to sink. It's essential to understand that this sinking tendency at a constant pitch attitude, as was pretty much the case with Northwest 6231, will result in a still further rapidly increasing angle of attack as the flight path becomes deflected downward, shown by the blue line here in the diagram. This is the beginning of what is termed a deep stall. Where the T-tail design suffers in such circumstances, however, is that due to the positioning of the tailplane in relation to the wing's turbulent wake, elevator effectiveness is greatly reduced, often to the point where the pilot's ability to counter this nose-up tendency is seriously compromised. Furthermore, this relatively slow air behind the stalled wing may sweep across the tail at such a large angle that the tail itself may stall. If this occurs, the pilot will lose all pitch control and thus will be unable to lower the nose and effect a recovery. The prognosis for the aircraft and the crew under such circumstances is pretty grim indeed. As the aircraft enters the deep stall, increasing drag reduces forward speed to well below normal stall speed, with the aircraft sink rate potentially increasing to many thousands of feet per minute. Indeed, with 6231 descending from nearly 25,000 feet in just 83 seconds, its average rate of descent was calculated at nearly 18,000 feet per minute. The aircraft will eventually stabilise in a near vertical descent, where the angle of attack may approach 90 degrees and the indicated airspeed may be reduced to 0. At such angles of attack, none of the aircraft's control surfaces are effective. This fact, combined with the extremely high descent rates generated, mean that deep stalls are virtually unrecoverable. It must be emphasised that this situation can occur without an excessively nose-high pitch attitude. Indeed, in some airplanes, it can occur at an apparently normal pitch attitude, akin to what the pilot might more commonly associate with cruise flight, and it is this quality that can be quite misleading to the unsuspecting pilot. If you'd like to research the subject matter still further, then this site's presentation of the Air France 447 accident is well worth a look. During its type certification process, the 727-200 series aircraft demonstrated stall characteristics which met the requirements of the civil air regulations. The significant requirements defined therein were firstly that at an angle of attack measurably greater than that of maximum lift, the inherent flight characteristics give a clear indication to the pilot that the aircraft is stalled. Typical indications are a nose-down pitch or a roll which cannot be readily arrested. Secondly, that the recovery from the stall can be achieved by normal recovery techniques starting as soon as the aircraft is stalled. Thirdly, that there be no abnormal nose-up pitching and that the longitudinal control force be positive up to and including the stall itself. Fourth, that a safe recovery from a stall can be effected with the critical engine inoperative. And finally, that a clear and distinctive stall warning be apparent to the pilot at an airspeed at least 7% above the speed at which the critical angle of attack will be reached. The certification stall tests conducted with the aircraft in all operating configurations and with the most adverse weight and CG conditions demonstrated that as the aircraft was slowed and its wing angle of attack was increased, the buffet produced by airflow separation from the wing provided a natural warning of impending stall. With the landing flap extended, however, the airspeed margin provided by the buffet warning was considered to be insufficient. Consequently, a stick shaker system was installed to provide an artificial warning for all configurations. In the clean configuration, that being gear, flap and spoilers all retracted, the stick shaker activated when the angle of attack reached a value of 13 degrees. When the aircraft was slowed further, natural buffeting occurred at angles of attack between 16 and 18 degrees. The buffet was described as quite heavy, when the speed was reduced to within 2 or 3 knots of the speed associated with maximum lift. When the angle of attack for maximum lift, which is about 22 degrees, was reached, there was a tendency for the nose to drop if the pilot relaxed pressure on the control column. Also, lateral stability was reduced noticeably, which increased the pilot's workload in maintaining wings level flight. During these certification tests, the angle of attack was increased to 25 degrees, after which recovery was effected by relaxing the pull force on the control column. With the use of engine thrust during recovery, the altitude loss was restricted to about 2,000 feet. Up to the onset of the stall buffet, the longitudinal control forces needed to effect stall entry increased as the angle of attack likewise increased. At higher angles of attack, up to and beyond the angle for maximum lift, the pull force required to maintain a nose-up pitching moment decreased. That said, once this back pressure on the control column was released completely, the aircraft's design facilitated a clear tendency for the nose to pitch down with an associated reduction in the angle of attack. Research showed that the Boeing 727 longitudinal control system is capable of developing the nose-up pitching moments needed to obtain angles of attack much greater than those associated with the stall. For an aircraft having the same weight, CG location and stabilizer trim setting as the accident aircraft, the manufacturer's analysis showed that an angle of attack of approximately 37 degrees could be attained if a continuous pull force was exerted to hold the control column fully aft. Like other aircraft which have horizontal stabilizers located near or on top of their vertical stabilizer, more commonly referred to as T-tail configuration, the 727 can pass through a range of high angles of attack where longitudinal instability occurs. This instability causes the aircraft, when no control force is applied, to pitch to even higher angles of attack. Longitudinal instability is caused by degraded horizontal stabilizer effectiveness when the aircraft's attitude is such that the horizontal stabilizer is enveloped by the low-energy turbulent air in the wake from the wings. When these high angles of attack are reached, a push force on the control column is required to reduce the angle of attack. For a 727 with an aft CG location and stabilizer trim in the cruise range, wind tunnel data showed that a nose-down pitching moment will decrease the angle of attack, and stall recovery can be attained by applying push forces to the control column. This being the case, the 727 satisfied all the relevant aerodynamic design criteria as stipulated by the US Federal Aviation Administration, and was thus certified for commercial passenger operations. However, in light of the deep stall characteristics of these T-tailed aircraft, some other regulators, namely the Civil Aviation Authority in the United Kingdom, chose to take a more prudent approach. When Dan Air in the UK notified the CAA of their intention to incorporate the 727-100 type into their fleet, the UK's regulatory authority refused them permission to do so unless a stick pusher was fitted to the aircraft. Whereas the stick shaker provided notice of an impending stall, it would not prevent one occurring. In response to its activation, it was the pilot's responsibility to lower the nose, thereby reducing the angle of attack. However, the stick pusher was an additional line of defence, whereby a pneumatic ram physically pushed the control column forward, were the pilot not to respond appropriately, or where his response was deemed insufficient to reduce the angle of attack to a safe value. Faced with the conflict of overspeed and stall warnings being presented at the very same time, evidence from both the flight data recorder and the cockpit voice recorder clearly showed that the crew of Northwest 6231 prioritised the former, believing that the deterrent buffet experienced as the airflow separated from the ring was in fact Mach buffet, a similar but less pronounced vibration felt as shockwaves develop on the upper surface of the wing as the airflow accelerates towards the speed of sound. Unbeknownst to Lagario and his crew, however, was the fact that the 727 type does not exhibit such high-speed buffet until the aircraft reaches speeds in excess of Mach 0.95, well outside the normal operating envelope. That being the case, instead of pushing on the control column to reduce the angle of attack and avoid the impending stall, they in fact pulled the aircraft into the stall, and failing to immediately identify the consequences of their actions, continued to apply back pressure to the control column, even after the stall had been entered. In context, why this is important is that had the FAA been as prudent as their British counterparts and insisted on the installation of a stick pusher, arguably this accident would never have happened. Theoretical relationships of angle of attack, velocity and drag were compared to the recorded rate of descent and load factors to determine the attitude of the aircraft after the stall. The comparison showed that the aircraft attained an angle of attack of 22 degrees or greater during the descent. Transient nose-down attitudes of more than 60 degrees would have been required to achieve the measured descent rate with an angle of attack of 22 degrees. The variations in load factors, which averaged about 1.5 G, were attributed to variations in the aircraft's angle of bank. The aircraft was probably exceeding 230 knots, with a nose-down attitude of about 50 degrees as it descended through 11,000 feet when the flaps were extended to 2 degrees. The momentary cessation of the stick shaker indicated that the angle of attack had been reduced to less than 13 degrees. The increase in vertical acceleration to 2.5 G was attributed to the aircraft being in a tight, nose-down spiral with a bank angle between 70 and 80 degrees. Another important function of the Pitot-static system is to facilitate an artificial field system whereby a resistance to the pilot's manual input on the flight controls, particularly at high altitude with rarefied atmospheric pressure, will act to prevent inadvertent overstressing of the aircraft structure. With the normally operating field system and a stabiliser trim setting of 1.2 units aircraft nose up, a pilot would have to exert a pull force of over 46 pounds or 20 kilos to achieve a 2.5 G load factor at an altitude of 5,000 feet and 250 knots. If, however, the elevator pitot system was blocked, as was the suspected case with 6231, so that the system sensed a zero indicated airspeed, a pull force of less than 30 pounds or 14 kilos would have produced the same load factor. After the aircraft had descended through 5,000 feet, however, it was noted that the load factor had reached a peak value of 5 G. This being the case, Boeing engineers stated that the aircraft's structural limits would have been exceeded at such high angles of side slip and load factor. As a result, they believed that the elevator assembly had failed, producing an aerodynamic flutter which could have in turn caused the elevator spar to fail and the left horizontal stabiliser to separate. With the aircraft at a stall angle of attack, when the horizontal stabiliser separated, an uncontrollable nose-up pitching moment would have been produced, which could have resulted in the angle of attack actually exceeding 40 degrees or more. Although the speed servo cams in all three engine fuel controllers suggested a crew selection of high engine power, the engines were producing very little thrust at impact, as evidenced by the absence of significant rotational damage. Probably the throttles had been advanced shortly before impact, but there was either insufficient time for the engines to accelerate, or acceleration was limited because airflow into the engine inlets had been distorted by the extremely high angles of attack and probable side slip. The conversations recorded on the cockpit voice recorder revealed that following ascent above 13,500 feet, the flight crew became concerned and puzzled by the apparent performance of the aircraft because of the indicated airspeed and the indicated rate of ascent. The flight data recorder, airspeed and altitude traces provided investigators an insight regarding these conversations. The airspeed trace increased rapidly after the aircraft ascended above 16,000 feet, while the rate of climb continued to increase and eventually reached a peak value of 6,500 feet per minute. Unbeknownst to the crew, their decision to increase the aircraft's rate of climb in an effort to temper the continuously increasing erroneous airspeed had in fact only aggravated the situation. The higher they climbed, the more the erroneous airspeed would overread. Boeing's analysis of the airspeed and rate of climb values that are registered above 16,000 feet showed that these values were incompatible with the aircraft's performance capabilities. Analysis showed that there was a direct relationship between the airspeed and altitude values. This relationship was based on the assumptions that firstly, the total pressure measured by the flight data recorder Pitot system remained constant after the aircraft ascended above 16,000 feet, and secondly, that the pressure measured by the flight data recorder static system varied according to the recorded altitude values. These assumptions were substantiated by the test which determined that the flight data recorder airspeed and altitude traces could be reproduced only if the total pressure to the airspeed indicator was held constant during ascent above 16,000 feet. Although the Pitot systems for the captain's and first officer's airspeed Mach indicators and the flight data recorder airspeed instrumentation are three separate and completely independent systems, it's reasonable to conclude that all three systems were sensing nearly identical and erroneous total pressures. This can be concluded because the flight crew made no reference to any difference between the airspeed readings on the captain's and the first officer's indications, and the first officer's reference to going 340 knots corresponded closely to the airspeed value recorded on the flight data recorder at that time, with the flight data recorder on the 727 exclusively recording the captain's airspeed indication only. Additionally, the near simultaneous activation of the overspeed warning system tends to prove that the first officer's airspeed was close to the value recorded on the flight data recorder when the aircraft neared its peak altitude. Thus, the erroneously high airspeed indications were caused by a complete and nearly simultaneous blockage of all three Pitot pressure systems. Moreover, since the only common elements among the systems were the design feature of the Pitot head and the environment to which they were exposed, the safety board concluded that the Pitot heads were blocked by ice, which formed around the heads and closed the drain holes and the pressure inlet ports. The conclusion is supported by the airspeed aberrations that were recorded while the aircraft was flying level at 14,000 feet, and by the moisture which was found in the Pitot heads when they were recovered and examined. Additionally, it is known that icing conditions existed in the area through which Flight 6231 was flying, and it is unlikely that any other type of blockage or malfunction would simultaneously affect the three independent systems. The formation of ice on the Pitot heads should have been prevented by electrical heating elements, which are activated by the Pitot heater switches located in the cockpit. The safety board concluded that the heating elements were never activated because the Pitot heater switches were not in the on position during the flight. This conclusion was substantiated by the position and condition of the switches in the wreckage, the internal damage to the right switch, and the lack of evidence that electrical current was present in the heater circuit to the Pitot head in the first officer's Pitot system at the time of impact. That said, initially the safety board had been at a loss to explain why the Pitot head heater switches were not placed in the on position before departure, as it was apparent that the flight crew had performed the pre-takeoff checks required by Northwest's operational procedures. It wasn't until the CVR was finally examined in order to establish exactly what transpired in the cockpit during those few critical minutes as the aircraft taxied out to the takeoff runway that the investigation team finally found the smoking gun they had been looking for all along. While reading aloud the checklist, the second officer called bugs, seeking confirmation that the correct reference speed bugs had been set for takeoff by both pilots. But before receiving a response from either the captain or the first officer, he omitted the ice protection call, referring to the engine anti-ice, which was the next item on the checklist, instead calling Pitot heat. The first officer apparently responded to both the omitted call and the Pitot heat call by saying off and on. But following the captain's response to the bugs call, the first officer asked whether the engine anti-ice was needed. Legario may or may not have responded with a nod or a hand gesture, but the sound of 5 clicks was recorded before the first officer returned to the task of setting his airspeed bugs. These 5 clicks, it was believed, may have been the movement of the Pitot heater switches to the off position, with the simultaneous movement of the engine anti-ice switches to the on position, a reversal of their normal positioning. This assumption was supported by the position of the engine anti-ice and Pitot heater switches found in the wreckage, the condition of the lights associated with the engine anti-ice switches, and the lack of any reference during the flight to the need for engine anti-icing. Thus the investigation team, having previously had their suspicions as to what had caused the accident, now had convincing evidence as to how the switch oversight had occurred in the first instance, and in so doing had solved the puzzle of Northwest 6231. Because of the flight crew's comments concerning aircraft performance and the absence of comments about possible instrument error or airspeed system icing, the safety board concluded that the flight crew attributed the high speed and the high rate of climb to the aircraft's relatively low gross weight and to an encounter with unusual weather which included strong updrafts. The flight crew's analysis of the situation must have been strongly influenced by these factors and by the fact that both airspeed instruments were indicating essentially the same values. However, the aircraft's attitude as it neared the top of its ascent should have warned them that the aircraft's performance was abnormal, because its near 30 degrees nose-up attitude was about 25 degrees higher than what would normally be expected in the climb. And at such a high nose-up attitude, it would have been impossible for the airspeed to continue to increase, even if influenced by extreme updrafts. Because the use of attitude reference is a fundamental of instrument flying, which is stressed in Northwest Flight Crew Training Program, the safety board concluded that the flight crew improperly relied on airspeed indications as a means of determining aircraft performance. Although the activation of the overspeed warning system probably reinforced the flight crew's belief that they were taking appropriate action, the operation of the stall warning stick shaker should have alerted the crew that the aircraft was actually approaching the stall. The first officer apparently misinterpreted the control column vibration produced by the stick shaker as Mac Buffet, because when the stick shaker began, he commented, "There's that Mac Buffet." The captain apparently agreed with his interpretation, because he then commented, "Pull it up." The almost simultaneous activation of the stall and the overspeed warning systems undoubtedly created some confusion. However, the difference between stall Buffet and Mac Buffet are substantial, and the former should have been easily recognised. Again, though, it appears that the flight crew relied almost exclusively on the airspeed indicators and their related warning systems to assess the aircraft's performance. Even after the stall, as manifested by the rapid heading change in the sudden descent, the flight crew failed to recognise the problem for a number of seconds. They continued to exert back pressure on the control column, which kept the aircraft at a high angle of attack. They were probably having difficulty with lateral control, and the aircraft entered into a spiralling descent to the right, during which time the actual vertical velocity increased rapidly, yet the forward airspeed of the aircraft through the relative air mass remained very low, as a result of the prolonged high angle of attack condition and the resultant drag it produced. The erroneous airspeed indications, the steep nose-down attitude, and the sensory sensations associated with the positive vertical acceleration forces undoubtedly contribute to the confusion which prevented the flight crew from recognising the true condition of the aircraft. Additionally, it was probable that the nose-down and banked attitude of the aircraft was so steep that the horizon reference on the attitude instrumentation was nearly hidden, making evaluation of the aircraft's true orientation extremely difficult. In light of the crew's handling difficulties, the captain most probably ascertained that they were aerodynamically stalled, and transmitted, "We're descending through 12, we're in a stall," as he called for the flaps to be extended to 2 degrees. Although selection of flap 2 will extend the minimum amount of trailing edge lift augmentation, it's the corresponding leading edge extension which makes the greatest impact on margin to the critical angle of attack. In other words, with the leading edge extended, the aircraft can attain a higher angle of attack before airflow separation and resultant loss of lift. However, this is coincidental and not the desired or correct initial crew response following entry into an aerodynamic stall. The intention following extension of the leading edge is to restore an adequate margin to the critical angle of attack, but only after action has been taken by the crew to first pitch the aircraft's nose down in order to achieve an angle of attack below the critical value, where the airflow can be reattached to the wing and lift restored. But in this regard, the 727, like all T-tail configured aircraft, is somewhat handicapped. In order to action this nose-down moment, the pilot must utilise the elevator, the primary flight control surface used to effect a change in pitch, which is located on the horizontal stabiliser. The the T-tail's Achilles heel, is that once the main plane is stalled, the turbulent airflow breaking off the wing has the undesirable effect of interfering with the tailplane, and in so doing reduces the elevator's effectiveness. So at a critical time, when the pilot desperately needs to pitch the aircraft nose down, the facility to do so has been greatly compromised. For this reason, many T-tails, including the 727, are fitted with a stick shaker. This is a small motor designed to vibrate the control column as the aircraft's angle of attack approaches its critical value. If no corrective action is taken by the pilot, entry into an aerodynamic stall will occur soon thereafter. Unless, that is, the aircraft is fitted with a further line of defence, namely a stick pusher. As the name would suggest, this stick pusher comprises a pneumatic ram designed to physically push the control column forward, thereby reducing the aircraft's pitch and subsequently its angle of attack just prior to the critical angle being reached. The irony of Northwest 6231 is that unlike 727s registered in many other jurisdictions around the globe, those registered in the US were not mandated to have such a device fitted. Arguably, had they been, in all likelihood, this accident would never have happened. Even after the pilots decided that the aircraft was stalled, the safety board believed that in reaction primarily to the high descent rate and their sensory perceptions, they continued to exert a pull force on the control column, contrary to the published stall recovery procedure. This being substantiated by the increasing vertical acceleration forces as the aircraft descent continued. With the angle of attack still above the critical value and no meaningful effort being made to level the wings, the aircraft continued to descend in a spiralling dive as these same pull forces kept the aircraft in an accelerated stall. Since the pitot heads for the elevator field system were probably also blocked by ice, the force required of the pilots to move the elevators would have been increased while the aircraft was above 16,000 feet. However, when the aircraft descend below this altitude, due to the erroneous reduction in airspeed, the same effort required would have been greatly diminished. As the descent continued below 5,000 feet, the airspeed sensed by the elevator field system was probably near zero. Consequently, significant overstressing of the aircraft structure could have occurred with very little physical effort on the part of the pilot. And indeed, this is what the flight data recorder confirmed had happened. As the aircraft descended to 3,500 feet, finally breaking out of cloud and being presented with the vista of the ground rushing up to meet them, the crew, without the benefit of a properly functioning artificial field system, had applied enough force through the control column to overstress the aircraft's tailplane, causing the left horizontal stabilizer to catastrophically fail. Thereafter, the aircraft probably rolled to a near wings level attitude, pitched up to an even higher angle of attack, and continued to descend in an uncontrollable stall until impact. During the safety board's investigation, incidents involving possible pitot-static system icing were reviewed. Although none of these incidents resulted in a catastrophic accident, it became clear that pitot or static system icing events during flight can and do occur. Also, the resultant effects on pressure-operated flight instrumentation can produce at least momentary confusion among many crew members. While all of the crew members involved in these incidents reverted to attitude flying until the cause of the icing could be eliminated, or instrument flight conditions no longer existed, it was apparent from these incidents that some pilots who understood the basic principles of airspeed measurement failed to analyse the possible results of a blocked pitot or static system. The pilots often failed to determine the proper reasons for an increasing airspeed indication, attributing such indications to unusual weather phenomenon, as indeed had been the case with Lagario and his crew. Although unusual weather phenomena such as mountain waves, extreme turbulence and vertical wind shear can produce significant airspeed deviations, these phenomena usually are of short duration and cause erratic or abruptly changing airspeed indications, rather than steadily increasing, steadily decreasing, or fixed airspeed indications. Also, the aircraft's attitude during encounters with these phenomena is important in determining airspeed trends and possible sources of error. Consequently, the safety board believed that potential Pitot-static system problems and attitude flying as a temporary remedy for these problems should be re-emphasized in instrument flying training programs. The safety board on foot of this accident accordingly making recommendations to the FAA. Decades later, accidents such as Air France 447 and Air Asia 8501 would suggest that much work still needs to be done. In a letter from the National Transportation Safety Board to the Federal Aviation Administration dated March 20, 1975, almost 15 months after the accident, the board stated that their continued investigation had conclusively revealed that ice had blocked the aircraft's pitot ports. A preliminary review of the evidence suggested that the crew had concentrated on air data information rather than the aircraft's attitude indicators, culminating in the aircraft's ultimate stall, loss of control and eventual impact with the ground. About 5 minutes before the rapid descent, the flight data recorder had noted 2 aberrations in the airspeed trace. These, they believe, were caused by the initial accumulation of ice in the Pitot inlet. The aberrations were verified by wind tunnel ice testing, producing traces similar to those recorded by the aircraft. The board revealed that it was aware of other incidents where aircraft had encountered difficulties while flying in freezing precipitation due to frozen pitot probes. In these incidents, however, the flight crew had recognized the problem and taken corrective action. They stated that evidence in the case of Northwest 6231 indicated that the heating elements built into the pitot probes, although serviceable and specifically designed to mitigate the possibility of ice accumulation, had not been selected on by the crew prior to departure. On foot of all they had learned to date, they were compelled to make the following recommendations. Firstly, that an operations bulletin be issued to all air carriers to stress the need for pilots to use attitude information when air data sources of information become questionable or unreliable. In other words, reasserting the basic principles of pitch and power. In response, the FAA stated that information bulletins already in circulation address the subject matter, but nonetheless conceded that additional advisory circulars were being considered. Secondly, the board recommended that an airworthiness directive, mandatory in nature, be issued requiring a warning system to be installed on all transport category aircraft, so as to highlight to crew when the pitot heating function was unpowered. In this regard, somewhat surprisingly, the FAA did not concur with the safety board's viewpoint. It was their belief that if implemented, such warning indicators on aircraft with cyclical type heaters would have potentially distracting consequences and thus in themselves could become safety-related issues. Admittedly, those systems with a straightforward on-off switch could be modified, but it was their opinion that such modifications were unnecessary, as adherence to checklist procedures would, they believed, mitigate the risks associated with any potential crew oversight. Yet incredibly, this was exactly what had happened to Logario and his crew. Finally, in an effort to mitigate against any similar future occurrence, it was the board's desire that the pitot heating system should always default to the on condition any time electrical power is applied to the aircraft. In response, the FAA were to some extent sympathetic, although they voiced concerns that retrofitting of current aircraft in service so as to ensure compliance would prove problematic on a number of fronts. Thus they believed that any such rule changes be more appropriately focused on new future design types. And so perhaps this is where the legacy of Northwest 6231 lies. Current practice dictates that anti-ice protection, particularly in the context of probe heating, will now either have to be selected on by the crew or, for example, in the case of the Airbus types, automatically selected following engine start. Furthermore, it's undoubtedly true that Logario and his crew had misidentified the situation they had found themselves in, and their subsequent response had made a bad situation worse. Yet in truth, they and their peers of the time were products of a system whose training focus on the effects of blocked pitot ports was arguably inadequate, due in no small part to the limited fidelity of the training device at the time. The lessons learned from the loss of Northwest 6231 were painful for both families and friends. But in such pain there may be solace in the fact that their loss was not in vain. The events surrounding the crash have served to enlighten pilots to the associated dangers of blocked pressure ports and continue to enhance pilot understanding of the environment in which they operate. Training modules have, over time, become more relevant and training devices more sophisticated, so that such events will be more readily identified by crews in the future, mitigating measures which hopefully will ensure that such catastrophic outcomes will never happen again. This was the complete story of Northwest 6231, lost on the evening of December 1st, 1974.